Here is a geometry problem from the International Math Olympiad. We have a bunch of points in the plane, like you see here. We consider all possible triangles on these points. Our goal is to show that at most 70% of these triangles are acute. In a previous video, I solved this problem. I actually showed a bound of 2/3. You don't need to have seen that video to understand the current one. In this video, we'll do much better. We'll first show that less than 61% of the triangles are acute. Then we'll improve the bound to 60%. Finally, we'll strengthen the bound to 56.15% when the number of points is large. That final bound is quite close to best possible. Furthermore, we'll show that this innocent problem about acute triangles is connected in surprising ways to some research conjectures in the theory of hypergraphs. Are you ready? Let's go! Here's an outline of the video. First, we'll talk about graph theory, in particular extremal graph theory. As an example, we'll consider the historically first result in extremal graph theory, called Mantel's theorem. Second, we'll talk about hypergraphs. We'll look at a conjecture in extremal hypergraphs called Turán's conjecture. We'll go over the best bounds known for this conjecture. Finally, we'll connect our work on hypergraphs to the original problem on acute triangles. Okay, step 1 is graph theory. When we talk about graphs in this video, we're not talking about this kind of graph. This graph is the graph of a function, but that's not what we'll mean by a graph. Instead, for us, a graph is a network. In this example, the graph has 10 points, often called vertices. It has 15 edges, each joining 2 points. This particular graph, called the Peterson graph, is frequently used for examples and counterexamples in graph theory. In our graphs, you're not allowed to have multiple edges between the same 2 points, and you're not allowed to have a self loop, an edge joining a point to itself. Next, we'll look at extremal graph theory. Suppose you have a graph on n points, where n is some whole number. What's the most number of edges you can have? This is part of extremal graph theory because we're trying to maximize or minimize some quantity, in this case the number of edges. For example, say we have 5 points. How do we create the most number of edges? Well, we should place an edge between every pair of points. Such a graph is called the complete graph. On 5 points, the complete graph has 10 edges. In general, the number of edges in a complete graph is n choose 2, the number of ways of selecting 2 points out of n. That number is given by the formula you see here. If we plug in n equal 5, we indeed get 10 edges. Okay, that's the simplest question in extremal graph theory. To make the question more challenging, we'll place restrictions on our graph. For instance, here is the triangle graph. It's the complete graph on 3 points. Suppose we don't allow any triangles in our graph. We'll get the class of graphs called triangle-free graphs. For example, here's the Peterson graph. Does it contain any triangles? No, it's triangle-free. Now we get an interesting question in extremal graph theory. Suppose we have a triangle-free graph on n points. What's the most number of edges we can have? As an example, suppose we have 10 points. The Peterson graph has 15 edges on 10 points. Is there a triangle-free graph on 10 points with more edges? Yes, as we'll see next. Here's a way to construct a triangle-free graph with lots of edges. We'll place half the points on the left and half on the right. We'll then add an edge between each point on the left and each point on the right. Such a graph is called a complete bipartite graph. Bipartite means the points are split into 2 parts. Does this graph contain any triangles? No. Given any 3 points, 2 of them will be on the same side, and those 2 points won't be joined by an edge. How many edges are there? It's n over 2 times n over 2, which is n squared over 4. For example, with 10 points, we have 25 edges. Here we've assumed that the number of points is even, but if the number were odd, then the same idea would work. We'll make the left and right sides as equal as possible. We'll still join every point on the left with every point on the right. In the odd case, the number of edges is n squared minus 1 over 4. We've constructed triangle-free graphs with many edges, but are they the extremal examples? It turns out the answer is yes. More than 100 years ago, Mantel, a Dutch mathematician, posed and solved this problem. he showed that every triangle-free graph on endpoints has at most n squared over 4 edges. This was the first non-trivial result in extremal graph theory. Next, I'll sketch one way to prove Mantel's theorem. The idea is to count the subgraphs on 3 points. What subgraphs on 3 points can a triangle-free graph have? Well, the subgraph could have 0 edges, or 1 edge, or 2 edges. The subgraph can't have 3 edges, because that would be a triangle, and triangles are forbidden. We'll count the number of subgraphs of each type. In particular, we'll focus on the subgraphs with 2 edges. We'll call that graph a wedge. A wedge has a central point and 2 edges coming out of it. Our proof of Mantel's theorem will rely on the following claim. Suppose we have a triangle-free graph with n points and m edges. We can bound the number of wedges in the graph as follows. I won't prove this claim here because we're really interested in hypergraphs, the next topic. But this claim has a short proof, on the left side counting based on points and on the right side counting based on edges. I'll put a link to a proof in the video description. Given this claim, we can prove Mantel's theorem quickly. Directly from the claim, we get this inequality. Solving for m, the number of edges, gives the following sequence of inequalities. And so indeed, the number of edges is at most n squared over 4. Mantel's theorem was the first result in extremal graph theory. It's since been extended in many ways. For example, instead of forbidding triangles, we could forbid another complete subgraph, such as the complete subgraph on 4 points or 5 points. In 1941, Paul Turán found exact results for such extremal questions, generalizing Mantel's theorem. Many years ago, I found a nice probabilistic proof of Turán's theorem. I'll put a link in the video description. Turán's theorem was generalized further by Erdős, Stone, and Szymanowicz. They showed how to obtain similar results on forbidding any forbidden subgraph. For example, say you forbid the Peterson graph as a subgraph in your larger graph. How many edges can you have? The answer, surprisingly enough, turns out to be pretty close to the triangle-free case, even though the Peterson graph is much more complicated than a triangle. Their result has been called the fundamental theorem of extremal graph theory. In summary, extremal graph theory has been quite a successful theory. For our original problem about acute triangles, though, we'll need to generalize graphs to hypergraphs. Remember, in a graph, every edge was a pair of points. Instead, in this hypergraph, every edge is a triple of points. I've drawn each edge as a light gray region, touching 3 points. For example, ABD is an edge. Because each edge is a triple, we'll call this hypergraph a 3-uniform hypergraph, or 3-graph for short. 3 graphs are the only kind of hypergraph that we'll discuss in this video. In the example shown, there are 9 points and 8 edges. In our discussion of graph theory, we talked about triangle-free graphs. What's the analog of a triangle in 1 dimension higher? I'd say a tetrahedron. Here's a tetrahedron. It's a solid in 3-dimensional space. It has 4 vertices, A, B, C, and D. It has 4 faces, each a triangle. For instance, BCD is a face. We can view a tetrahedron as a hypergraph. The tetrahedron hypergraph has 4 points, also A, B, C, and D. Each face of the tetrahedron solid maps to an edge of the hypergraph, a triple of points. For example, BCD is an edge of the hypergraph. Let's look at the tetrahedron hypergraph again. It has 4 points. It has 4 edges. It's the complete 3-graph on 4 points. Just like we discussed triangle-free graphs, we can talk about tetrahedron-free hypergraphs. We'll ask a similar question. If a tetrahedron-free 3-graph has n points, what's the most number of edges it can have? For example, here's a tetrahedron-free hypergraph. It has 9 points and 8 edges. Can we have more edges in a tetrahedron-free hypergraph on 9 points? Yes, way more. We can have 54 edges, as we'll see next. Here we'll construct a tetrahedron-free hypergraph with many edges. we'll divide our endpoints into 3 sets as balanced as possible. Call the 3 sets A, B, and C. For each point in A, each point in B, and each point in C, we'll create an edge on that triple of points. Here I've drawn one such edge. You'll have to imagine all the other edges. But those aren't the only edges we'll add. For every 2 points in A and every 1 point in B, we'll create an edge on that triple of points. I've drawn one such edge. We'll do the same for every 2 points in B and 1 point in C. Finally, we'll do the same for every 2 points in C and 1 point in A. Does this hypergraph contain any tetrahedra? No. To see why, consider any 4 of its points. If 3 of the points were in the same set, A, B, or C, then those 3 points wouldn't form an edge. So we may assume that A, B, and C each have at most 2 points. The 4 points must then split into 2, 2, 0 or 2, 1, 1. And we can check that neither split gives a tetrahedron. Okay, how many edges does this hypergraph have? The edges come in 4 types. How many edges are of type ABC? The answer is n over 3 times n over 3 times n over 3, which is n cubed over 27. How many edges are of type AAB? The answer is n over 3 choose 2 times n over 3, which is n cubed minus 3n squared over 54. The same is true for BBC edges. The same is true for CCA edges. Altogether, the total number of edges is 5n cubed minus 9n squared over 54. This calculation assumed that n is a multiple of 3. Even if n weren't a multiple of 3, though, we'd get roughly the same number of edges. Here we've counted edges. Instead of a count, we're often interested in the fraction of edges. We'll call this fraction the density. A 3-uniform hypergraph has at most n choose 3 edges. So the density of a 3 graph is the number of edges divided by n choose 3. For example, let's look at our construction of a tetrahedron-free hypergraph. How dense is this hypergraph? Let's calculate. We see that the density is about 5/9. Our hypergraph has about 5/9 of all possible edges. Is that the highest density possible for a large tetrahedron-free hypergraph? No one knows. That's a famous unsolved problem. Here is the tetrahedron conjecture, due to Paul Turán from 1961. He conjectured that in a tetrahedron-free 3 graph on n points, there are at most 5n cubed minus 9n squared over 54 edges. Basically, Turán conjectured that the construction with 3 sets that we showed earlier is optimal. Decades later, we still don't know whether his conjecture is true. We think it's true, and researchers have made impressive progress, but we don't know the final answer. Let me say a little about Turán. He was born and raised in Hungary. In 1941, during World War II, he generalized Mantel's theorem in graph theory to all complete subgraphs, as we mentioned before. Being Jewish, Turán did this work while imprisoned in Nazi labor camps from 1940 to 1944. His work kicked off tons of research in the new field of extremal graph theory. 20 years later, he posed his tetrahedron conjecture on hypergraphs. These hypergraph problems are much harder than the corresponding graph problems. Besides Paul Turán, I would like to mention another Paul. Here's a photo of Paul Erdős and Paul Turán. They were lifelong friends and collaborators, writing 30 papers together. Erdős was known for posing problems and offering money for the solutions to those problems, almost always his own problems. But he liked Turán's conjecture so much that he offered $500 for a solution. More importantly, if you were to solve Turán's conjecture, you would become famous within the math world. Even though Turán's conjecture has not been solved, we've made a lot of progress on it. I'd like to share some of that progress with you. First, we'll define a sequence of numbers, the Turán numbers. Let T of n be the maximum number of edges in a tetrahedron-free 3 graph on n points. As an example, T of 3 equals 1 because we can have one edge on 3 points. Also, T of 4 equals 3 because on 4 points we can have 3 edges, but 4 edges would be a tetrahedron. What about the other Turán numbers? Thomas Spencer calculated the Turán numbers up to 13 points. Here they are. For up to 10 points, he did so by hand, but for the last 3 he needed a computer. His numbers confirm that the 3-set construction we gave before is optimal for up to 13 points. These first few Turán numbers will give us bounds on all the higher Turán numbers. Let's see how. Say we want to bound t of 14, the smallest unknown Turán number. I claim that the following inequality is true. In other words, for tetrahedron-free 3 graphs, the maximum density on 14 points is at most the maximum density on 13 points. Let's see why. Suppose we have a tetrahedron-free hypergraph on 14 points. I've drawn one such edge, one on such a hypergraph. Density is the probability that a random triple is an edge. Now consider all 14 ways of removing one point from this hypergraph, as shown. We can check that the original density is the average density of these 13-point subgraphs, but the 13-point densities are all at most t of 13 over 13 choose 3. And so we've shown that maximum density is decreasing. It follows that for every n at least 13, t of n over n choose 3 is at most t of 13 over 13 choose 3, which we can calculate. Therefore, the density is just under 60.84%, less than 61%. We can do better. Let's look at t of 14 again. We had the following density inequality. Calculating shows that t of 14 is at most 221.45 repeating. Since t of 14 is a whole number, it's actually at most 221. And so the density is at most 60.71 something percent. We got a free improvement by taking advantage of the fact that the Turán numbers are integers. We can keep going like this to improve the limiting density. We can show that the limiting density is at most 60%. Specifically, we can show the following inequality. The proof is by induction, using decreasing density and the integer constraint we just talked about. 60% is good, but we can do better. Rahul Barber proved that the limiting density is at most 0.5615. I spoke with Barber, and he may have improved the bound to 0.5597, but since he hasn't rigorously proved that bound, we'll stick to his proven bound of 0.5615, or 56.15%. That's quite close to the 5/9 lower bound we know from our 3-set construction. As to how this density bound was shown, I can only give a brief indication. It uses a method due to Sasha Razborov called flag algebras. Remember in the proof of Mantel's theorem, we counted the number of subgraphs on 3 points? Well, here instead, we'll count the number of subgraphs on 6 points. First, let's enumerate the tetrahedron-free hypergraphs on 6 points. Here is a tetrahedron-free 3 graph on 6 points, and here are some more. Are there any others? Yes. Altogether, there are 964 such hypergraphs. The flag algebra method will count how many of these subgraphs can appear in a large hypergraph, and in particular will develop inequalities among the various subcounts. 964 hypergraphs is large enough that a computer was used to determine the best inequalities. Okay, that concludes our discussion of hypergraphs and Turán's tetrahedron conjecture. For our final step, let's see what these hypergraph results have to do with the acute triangle problem that we started with. Remember this problem from the International Math Olympiad? We have 100 points in the plane. We consider all the possible triangles on these points. We want to show that at most 70% of the triangles are acute. This IMO problem is about 100 points, but we may as well consider any number of points, say n points. Given a whole number n, let a of n be the maximum number of acute triangles among n points in the plane. For example, a of 3 is 1. Just take 3 points that form an acute triangle. What about 4 points? the 4 points here have 3 acute triangles on them. So A of 4 is at least 3. Let's show that A of 4 is at most 3. 4 points in the plane will look like one of these two figures. Let's mark some of the angles. From these diagrams, we can check that at least one angle is not acute, which means that at least one triangle is not acute. In other words, at most 3 of the 4 triangles are acute. So A of 4 is at most 3, and by what we've shown before, that means A of 4 is exactly 3. With 4 points, we can't have a complete set of acute triangles. I promised earlier to connect acute triangles and hypergraphs. Here's the connection. Suppose we have a set of points in the plane, like these. We'll form a hypergraph. Each of these points in the plane will be a point in the hypergraph. For each acute triangle on these points, we'll create an edge, a triple of points, in the hypergraph. For instance, BCD is an acute triangle, so BCD will be an edge in the hypergraph. We'll call this the acute hypergraph of the points in the plane. The number of acute triangles is the same as the number of edges in this hypergraph. We know that any 4 points in the plane have at least one non-acute triangle. That means any 4 points in the hypergraph are missing at least one edge. In other words, the hypergraph doesn't have any tetrahedra. So we're counting the number of edges in a tetrahedron-free hypergraph. That's the Turán problem we studied before. Recall the Turán numbers T of n and the acute numbers A of n. By what we've just said, A of n is at most T of n, so we can use the upper bounds we know on the Turán numbers. Remember our 60% bound? It automatically applies to A of n. For example, suppose we have 100 points, as in the IMO problem. Then A of 100 is at most 97,040. As a percentage, less than 60.013% of the triangles are acute, a much better bound than 70%. Remember our best asymptotic bound on T of n? Barber showed that the limiting density is at most 56.15%, so the same bound carries over to the acute numbers. For sufficiently large n, at most 56.15% of the triangles on n points are acute. What about lower bounds on the acute numbers? Previously, we showed that the Turán densities are at least 5/9. Does the same bound hold for the acute densities? Well, not automatically. At the moment, all we know is that A of n is at most T of n, not the other way around. Nevertheless, we'll show that the acute density is at least 5/9. Here is the construction. We'll try to mimic our 3-set construction for hypergraphs using points in the plane. We'll start with 3 points that form an acute triangle. Call the points A, B, and C. The angle at B will be just under 90 degrees. The angles at A and C will equal each other, just over 45 degrees. We'll place n over 3 points each near A, B, and C. Namely, the n over 3 points near A will be on a little circular arc with center B. The n over 3 points near B will be on a little circular arc with center C. Finally, the n over 3 points near C will be on a little circular arc with center A. We'll arrange these points so that every triangle of the form ABC is acute, every triangle of the form AAB is acute, every triangle of the form BBC is acute, and finally, every triangle of the form CCA is acute. As in our 3-set construction of tetrahedron-free hypergraphs, that will make just over 5/9 of the triangles acute. So, let's summarize what we've learned about the acute triangle problem. We've shown that the maximum fraction of acute triangles is between 5/9 and 56.15% when the number of points is large. Because 5/9 is 55.5 repeating percent, we've sandwiched the limiting density in a pretty tight interval, but the final 1% is eluding us. We think the limiting density is 5/9, but we haven't proved it. Can you, dear viewer, solve this open problem? One way is to prove Turán's tetrahedron conjecture, or maybe there's a way to solve the acute triangle problem without fully settling Turán's conjecture. Well, I hope you enjoyed this journey into geometry, graphs, and hypergraphs. In the video description, you'll find several links and references. Thanks for watching.